All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We're going through a bunch of problems last time, and I asked you guys to try a couple more at the end. Let's actually see if I can get this up. Okay, all right, there we go. All right, so last time we were just going through a bunch of different problems. We did the birthday problem, we did the sampling with and without replacement problem. We spoke about briefly, we went over the Bayes theorem problem. And another way that we could have done that. So that's Bayes theorem version 1. And yeah, so now there's one more technique I'm going to teach you in regards to taking computing probabilities. But as far as in general, what we would be doing at this point is just you going over a bunch of problem sets and practicing what you already know. So you can start that. And I believe, so yeah, there's another problem set 3 that I will, it's in the notes. And you can also find it on the class website where there are a lot of problems on that. This is probably one that I will leave for you guys to try for tomorrow after I teach you the new kind of probability technique. This problem was actually something that I put on an exam before. So it's like a final exam. So it's a nice problem to practice once you actually understand what I'm going to teach you today. But yeah, you'd have a lot as well as, so we've had 3 problem sets for probability so far. I've done most of the problems on set 1 and 2. It would be a good exercise to go over set 1 and 2 and actually make sure that you can do the problems in sets 1 and 2. And yeah, and set 3 now that you have it, right? So you can practice these on your own. But for now, we are going to go through these together. So let's actually get into that. Problem 7 is what's going to introduce the new topic for us, but scale is off again. I don't know what's going on. All right, so let's just do this. Let's see what we can get here. So problem 6 on handout number 2, this is. Business majors, that's you guys, are required to take Math 1108 and 1109, right? So you should know that you have another math class. Yay! Suppose on average, 15% of students get an A in Math 1108 and 10% get an A in Math 1109. These are just making up numbers, don't freak out. Also, we know that 23.5% of students get an A in one course or the other. What fraction of students get an A in both courses? And what is the probability that a student who gets an A in Math 1108 will get an A in Math 1109? And is getting an A in both classes independent? Right? So these are the questions we're going to answer. So we know the drill for getting into probabilities. So the first thing we kind of do is we kind of set up our variables, which in this case is going to be our events. So let's actually do that. I don't want to use A and B because getting an A is a part of the problem. So we'll use something like X and Y. Okay, so we set that up. Now, once we set that up, we can also now start talking about what are the given probabilities? Like, what do we know? What were we told so far? Okay, so now we can talk about what's given. We know that 15% of students get A in 1108. So what they just told us is the probability of you getting an A in 1108 is 15%. That's 15 out of 100, in case you want to think of it as a fraction, which is 0.15. We also know that 10% on average get an A in 1109. And we know that 23.5% get an A in one course or the other. So what is that probability? What is that probability? What are they just telling me? P of what? That 23.5% would be probability of what?
Is it the intersection of X and Y?
You mean X and Y?
Yeah.
How do you normally translate this symbol?
Isn't it intersection?
Right, but what does intersection mean?
It means that, or.
Intersection means or?
Well, I know that like it's either or, like it's not and.
It's intersection means that both would have it, right? Intersection means it's what they have in common.
Okay.
So it would be and, right? Because it's what X and Y have.
So
right?
is it union then?
So it's the union. Intersection means and. Right? So X and Y. Right? What we actually want here is the union. That is or. And by the way, normally this usually means inclusive or. Yeah, so it means it's in one or the other or both, right? So now we are told that that is 23.5%. So that's that. Okay, so make sure we have that. And means intersection. You want to think of it as and U means union. Want to think of it as or, right? The interpretation come from set notation. So when we covered sets and we looked at and or, and the and with the n looking thing was when we looked for what was in all sets at the same time. And the union, the U, was when we look for anything that was in any of the sets in the computation. So that's important for you to know. So so this is what is in all sets at the same time. And this is what is in any set, one or the other, or both. Right, so that's from set theory, set notation. So that's what it means. So we were told the or here, because you see it says or the other in the question. So that's union. So now, looks like a bunch of people are having trouble with their internet today. A bunch of people keep getting kicked out and having to come back in. All right, so that's what we were told. Now, in part A, what do we want? And so part A is what fraction of students get an A in both courses? What do we want here?
This is the intersection now.
This is the intersection because you want and, right? To get an A in both courses means you get an A in 1108 and in 1109, right? So here, you actually want the intersection. So if you know each individually and you know the union, how would you get to the intersection? Do you remember anything that connects all of these? What would connect all of these? Or how can I find the intersection? Do you have a formula for it? I mean, and just means you do that, right? Is that true? This and this, you multiply the probabilities. Is that true? Yes, no, maybe so. Okay, so I don't think it was that class, maybe the one before. It was the one before that. No, it was the one before that. It was a while ago. It's a good thing we're having this refresher because we talked about this stuff a while ago. But of course, test 2 and the final is coming up. So that's why I'm giving you these random problem sets where you have to pull on random pieces of information. So we have this. Probability of A and B equals probability of A times the probability of B, but in a very specific circumstance, only if they're independent, right? So that applies to independent, right? We also, which at this point, we don't know if they're independent or not, so we can't assume that. A and B are mutually exclusive, and it meant this, right? We did this 3-4 lectures ago. So the and, using the intersection for multiplication is not true in general. It's true if we know that they're independent. So we can't really use that here. Is there anything that we know works in general, no matter what, that connects or and together? Okay, so there was something called the law of disjunction. Which is again, way back. We proved this with the help of the inclusion-exclusion principle. Very important rule. We've actually used it a few times. So this is the one that tells you that OR is equal to the sum of the probabilities. Probability of X or Y is the probability of X plus probability of Y minus the probability of X and Y. So here's a formula that connects OR and it also includes the probabilities of the individuals. Of course, for 3 sets, the formula gets a lot more complicated from 3 sets onwards, but we only need to know it for 2 sets, at least so far. Like I don't, if I'm going to give you, like this is a formula I'd expect you to know for 2 sets. If I ever have, which I don't think I will, but you never know, the mood might strike. If I ever have the inkling to talk about the union of 3 sets, I would give you the formula at that point. But yeah, we have the law of disjunction, which tells us that is true. So this means the probability of the intersection, I can just solve it for it in this equation, right? By just moving the intersection to the left side and moving the OR to the right side, we can get that. And we know what each of these are, right? So probability of X is 0.15. Probability of Y is 0.10. Probability of OR is 0.235. So that's 0.25 minus 0.235. So it's like 25 minus 23.5. You get like 1.5. So it's like 0.15 there. Right. So that's the fraction of students who will get an A in both courses with these makey up numbers. Or you can, if you want to write it as a fraction, 15 over 1,000. Okay, so that was part A. Part B. What do we want in part B? So if you look at part B, what is the probability that a student gets an A in Math 1108? That a student that gets an A in Math 1108 will get an A in Math 1109. What is that asking me for? What probability? So these are the principles. As you're seeing, we define our events. We write on the probabilities that we're given. Then we have to interpret the question as to which probability we want to find. Once we know what we want to find and we know everything that we're given, we now just look for a formula that connects all of them and you apply it, right? And of course, the formula needs to work in the context that you're doing it. So there are some formulas that only work when you're independent. Some formulas only work when you're mutually exclusive. Some forms work in general, so you need to know them, right? Like Bayes' formula and the law of disjunction work in general. Those are true in general. But the thing like probability of A and B equals the probability of A times probability of B, that only works for independence. So it has to be independent before you do that. The probability of A or B equals the probability of A plus probability of B, that only works for mutually exclusive. They have to be mutually exclusive for you to do that. Yeah. So part B, what is it asking us for though? Probability of what? Probably that the student who gets an A in Math 1108 will get an A in Math 1109. What is that asking me? You can go on and take a guess. Because we want to know where your intuition is and if it's telling you the right thing.
Is it the union of the two?
Well, what does union translate to?
Oh, never mind. I mean intersection. And yeah.
Okay. Well, it's not and I know why you would think it's and, but we also already found and, so it wouldn't be and. You look at how it's phrased. It's phrased in a very particular way. It didn't say what is the probability that a student will get an A in 1108 and in 1109. That's not what was asked, right? The question says, pretend someone gets an A in 1108. What is the probability that they will get an A in 1109? Right, so that's very different. It's not just and. Can you think of anything else that would kind of cover that scenario? Because there's a difference here. Remember when we were doing the two girls problem, where I said, oh, what's the probability that they have two girls? It was a quarter. And then I said, what is the probability that they had two girls if we know that the older one is a girl? And they aren't the same thing. They got a different answer, right? In fact, the probability of the older one being a girl was like a half, right? So probably if the first is a girl and the second is a girl, is different from saying the probability that we know the older one is a girl was the probability that the second one is also a girl, right? So even though in both cases, you kind of end up with an and kind of situation because you'd have both girls, but the way it's phrased, the amount of information you have in the beginning changes, which means the sample space changes, which means your probability changes. So, well, usually your probability would change. So, yeah, what kind of probability covers that situation? Where we know an event occurred and we want the probability of some other event occurring. So it's not like just some student who hasn't taken either course and I want to guess what are the chances that this student is going to get an A in both of them. I'm now dealing with a student who has been through 1108. They took it already. And then he's going to take the second one. And now I want the probability. What is the probability that given that he passed the first one, he's going to pass the second one? Right? Which that was even more suggestive language. So what are we looking for? Do you think? What else comes to mind? Come on, talk to me. Test 2 is a week from tomorrow, so it'll benefit both of us to know what you guys understand from what you don't. So you'll know what to focus on when studying over the weekend. Any probability that deals with that situation? Which we spoke about last class and the class before that, I think. Maybe even the end of the class before that too. It was definitely involved in Bayes' theorem. What kind of probabilities what kind of probability is Bayes' theorem used to find? So here, what I want you to realize is that the student got an A in 1108. So event X has occurred. And we want the probability that event Y will subsequently occur. Right? So this means we want any last guesses?
This would be the intersection, right?
No, that was suggested earlier. Because it's not and, right? It's not the probability of getting an A in 1108 and 1109. That's not what was asked. We're asking someone already got an A in 1108. That's in the past. We know they got an A in 1108. Now I want to know what is the probability that they're going to get an A in 1109 in the future. That's not and.
So would it then be or?
It would not be or either, because or would be me asking, what's the probability that they'll get an A in one or the other, right? That would be union, that would be or, right? And in which case, that wouldn't even be a question anymore because I know they already got an A in one, so the or would already be satisfied because they got it in one. So this is a very important kind of probability. It's the conditional probability, something you need to know. So this is the probability of Y given X is what's being asked for. So it's right here. Probability of A occurring given that B has already occurred. This is the probability of A given B. It's not the same as and because they have a different sample space. The and probability will have the original sample space, but the conditional probability will have a reduced sample space because you'll know that something will occur already. So your total possibilities can be dwindled down. Your set of total possible outcomes is going to be less than or equal to what it was before because you know an outcome certainly happened. So now you can exclude certain outcomes. So just like in the two girls problem, where when I told you the older one was a girl, it excluded the possibilities of the firstborn being a boy, which so the cases boy, boy and boy, girl were now eliminated from the possibilities. And so now you only had girl, girl, and girl, boy, in which case now it's 1 out of 2 that you have 2 girls. Whereas originally, the probability of 2 girls would be 1 out of 4, because without me giving you the information that a girl already occurred, you now have 4 possibilities: boy, 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 girl, 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 boy, right? But by me telling you something already happened, now reduces the possibilities, right? That's not the same as and. It's what we call a conditional probability. That's this. So this is the probability Y will occur given that X already occurred. So it's very important that you pay attention to the language here. I do realize that it's very common, or it might even be intuitive for you to think that I'm asking about the and. But as I mentioned, you do not want to use your intuition to get through probability. It's not going to work. Don't do it. Look at the definitions, look at how we would do certain things, look at how the question is phrased, and make sure you're doing that. I didn't ask for an A in 1108 and in 1109. I did not ask for what is an A in both 1108 and 1109 or anything of that sort. I asked for the A in 1108 happened already. What is the probability that you'll get an A in 1109? That is a very different type of question. That is a conditional probability question. Whenever something already happened in the past and you want to find the probability of something else happening, this is conditional probability. Do not think and, do not think or, right? So that's what we actually want. Now, we took a lot of time to get through that, so let me just go quickly through the rest. I won't ask. We remember the formula for this, hopefully. This is the and divided by the probability of that. We know the and, we found that already, so I wouldn't have asked to find it again. So this is 0.015. And probability of x, that is 0.15. Okay. Of course, you can move the decimal place 3. So this is going to be 15 over 150. That's 1 out of 10. So this is 0.1. C. Is getting an A in 1108 independent of getting an A in 1109? Independent means one won't affect the other, but you do not want to use your intuition to determine that again. So how do we know that things are independent? Are X and Y independent is what this is asking. But we know, hopefully, what that means. Do we do it over here? No, did that before. Independent means one of these 3 equations. Well, it would mean all of these 3 equations hold, but you'd only need to verify one of them. Notice that the first one, probability of A given B equals the probability of A, is one way to know that something is independent. If B already occurred, has no change in the probability of A occurring, then that means they're independent. So what we can notice here is note the probability of Y given X is 0.1. And we've seen that 0.1 before. Notice that that is also the probability of Y. So this happens to give us the same number as the probability of Y. So the probability that Y occurs given that X occurs is just the probability that Y occurs, which means I don't care whether X occurred or not. The probability of Y is not going to change. So yes, they are independent. Another way to do this, you could verify it with another equation, or we could verify that the probability of X and Y is the probability of X times the probability of Y. So if we could say, note, probability of X times the probability of Y, what is that? Probability of X is 0.15. Probability of Y is 0.1. If you multiply those, you get 0.015. And if you look at the probability that we got for and, you'd realize that was 0.015. So these are actually the same. So the probability of X and Y is the product of the probabilities. So this means that X and Y are independent. So you could also do it that way. But here you could do it without any further calculations. Just look at your answer to part B and compare it to your answer to to the given information, and you'd realize that you have independence. Assuming you remember the equations that tell you when you have independence, and you would then know how to do that. D, bonus. Are X and Y mutually exclusive? So here you would just note, probably if X and Y is equal to 0.015. Now, what's important about that number is not necessarily the number itself, but what's important is that it's actually not 0. So X, Y are not mutually exclusive. So remember, mutually exclusive, what that means is the probability of the intersection is 0. That's the definition of mutually exclusive. Covered a couple classes ago. So that was a very important question with some very important concepts that I'm definitely going to test you on. So it's a good refresher. Right now, though, I want to do something new that we'll just have to get through quickly. So I'm just going to introduce a new concept. I did this with a Q&A, but we don't have time for that anymore. So a basketball player makes 70% of the free throws he attempts. Suppose he takes 10 free throws. The outcomes are all independent of each other. What is the probability that he makes all 10, or that he makes exactly 2 of them, or that he makes between 3 and 5, or that he makes at least 1? Now, this is kind of complicated. For exactly 2, for instance, not only do we have to worry about probability, but also how the event can occur. Right? Now, what do I mean by how the event can occur? Well, if it has 10 free throws, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are actually a bunch of ways that he can get 2. Right? Right? So he can have, he can get, come on, iPad. He can get this one and this one, or he can get, say, this one and that one, or he can get this one and this one, or he can get this one and this one, right? Or any number of things, right? So besides the probability, you also need to figure out how is he getting the two, right? Which makes it complicated. So now you're going to have to do counting while you're doing probability, besides the counting that you need to do for the probability. Well, here the probability is kind of given. You're given the 70%. So the probability itself, the counting, you don't really need it there. It's given to you. But now the idea is, how do we do this in this kind of structure? Now, solve a smaller subproblem. Suppose he takes 3 free throws. Let's cut it down to 3, because that's going to be easier. What is the probability? He makes 2. Well, now with just 3, it's going to be a little bit easier to count, and you can see the process a little bit better. So what we will do is think about how can he make 2? So let check means he makes it. And X means he misses. So he can make the first 2 and then miss the third. Or he can make the first and the third, but miss the second. Or he can miss the first and then make the last 2. Now, you can notice that this is all possible ways to make 2. And I don't want to actually count that specifically here, like when he has 10 or more, because that's going to take forever. So we want a principle that can help us to count this. Now, we do have a principle that was introduced a long time ago. I want you to notice we need to choose 2 spots from 3 spots for him to make the shot. And notice, I don't care about the order, right? I don't care which order he makes the 2 in, just that he makes 2. So this is 3, choose 2, okay? Which is going to be 3 ways, which by just enumerating, you can see that there are only 3 ways. Now, once you know that's the number of ways it can happen, now you start figuring out the probability of each. So for the first one, you can figure out, okay, what is the probability of this happening? Well, they're independent, so it means we can multiply the probabilities. So he makes it with a 70%, he makes the second one with a 70%, and he misses the third one with 30% chance. So he makes the first and makes the second and misses the third, and probability means multiplying the probabilities, so you can get that. So this is 0.7 squared times 0.3. Similarly here, he would have 0.7, then he misses, then he makes the last one. again, you get 0.7 squared times 0.3. With independence again, he will miss the first, make the second, make the third. You'll notice that again, it's 0.7 squared times 0.3. Obviously, there's a pattern. On top of that, you can know ways to make 2 out of 3 is this way, or this way, or this way. And I want you to note these are mutually exclusive. He can't do both of these scenarios at the same time, right? So he can't meet the first and the second and at the same time meet the first and the third. That would mean he made all 3, right? So he can't do both of these at the same time. So they're mutually exclusive. And what that means then, we can add the probabilities. To find the probability he makes any one of these situations. That's the or. He can do this or that or that. So you can add the probabilities. So that leads you to this idea where we're just going to add these guys up. So we have a common term of 0.7 squared times 0.3, well, to the 1. I'm writing that for emphasis. And I'm adding it to itself 3 times. 3 times happens to be 3 choose 2, the number of ways he could actually make that. And notice that here, this means he has 2 successes and 1 failure. So So that kind of leads us to, and 3 is the number of attempts. And this leads to what we call a binomial probability. So then I'm going to just give you the formula for this. Right? So bi means 2. So this is a situation when you only have 2 kinds of outcomes, success or failure. So suppose an experiment is being repeated. And 1, it is repeated n times. 2, each trial is independent. And 3, there are only 2 kinds of outcomes. Success or failure. A lot of things in life happen with that. You just care, did we do it or not? Did we make it? Did we have the success or not? So let's say here, the probability of success is P. And here, the probability of failure is Q, which of course you would know is 1 minus P. If we let X equals the number of successes, then that leads us to a nice formula that we sort of figure out the form of it above with combinations. Then the probability that X equals K is going to be equal to N choose K, P to the K, Q to the N minus K. Okay. So now I want you to notice in the problem that we were given, N equals 10, P equals 0.7, and Q equals 0.3. And then makes all 10 means K is 10. Makes exactly 2 means K is 2. Makes between 3 and 5 means K can be 3, 4, or 5. Makes at least 1 means K can be 1 or bigger, 1, 2, 3, 4, 5, all the way up to 10. Which is going to be annoying to use this formula, even though you have a nice formula. So I'd probably use the complement for that. So now back to this. So I want you to try this now. And I'll leave another problem for you to try for next time. It's over here. So these are going to use binomial probabilities to solve both these problems, because you'll notice that they will have the prerequisites. Okay. This one, by the way, is an old final problem. So if you want to know what a problem like this would look like on a final, that's an example of it. Which it looks complicated, but once you recognize it's a binomial probability problem, it shouldn't be that bad. But we will stop there. We are way over time. But thank you for your time and attention. Hopefully you guys also realize some things you have to pay attention to for the test next week and for the final after that. But yeah, if you haven't met with me in your projects, there are still some time slots available today. So try to get those in. And I think that's it. All right. So I will see you guys tomorrow in the next one. Ciao.